In this video, we're going to discuss moments and center of mass. So moment is just the tendency of a system to rotate, and it's usually about an axis or a point. I think the easiest way to think of this is in terms of like a seesaw. Let's say you've got a seesaw, it looks like this. You've got one child sitting on this end, and this child is, let's say, 2 meters away from the middle, and this child has a mass of 30 kilograms. And then you've got another child sitting over here. Maybe this child has a mass of 20 kilograms, and he or she is also sitting 2 meters from the center. The question is, well, if this is my balance point, if these moments aren't exactly the same, this whole system is going to have a tendency to rotate. So we're going to have a non-zero moment here. Now I just want to ask you, just intuitively, like, if this is our system, I've got a 20 kilogram kid over here 2 meters away, and I've got a 30 kilogram kid over here 2 meters away. What is the tendency of this thing to rotate? Is it going to rotate this way or that way? You probably said this way, right? It's going to rotate down in this side because this child weighs more than that child. Say, okay, well, if they're at exactly the same distance from that center point, but this child weighs more, then we're going to have a tendency to rotate in this direction. But what if one of them was closer? What if you had, let's say you had 2 children that had exactly the same weight. This one has a weight of 20 kilograms, and this one has a weight of 20 kilograms. But this one is 2 meters from the center, and this one, this is not to scale, is 3 meters from the center. Let's put the 3 on this side and the 2 on this side. Which way is it going to tend to rotate now? Well, if the masses are the same, but this guy is further away, somehow that's going to, because he's further away, the system is going to tend to rotate like this. So if they have the same distance, but this mass is larger, it's going to rotate in this direction. Or if they have the same mass, but different distances, it's going to rotate in the direction of the larger distance. So that's the principle. Let me give you a definition. The moment of a mass m about a point P. So here's my point P, and here's my mass m, and this distance from P to M is x units. The moment is just going to be that mass times that distance. And that distance, x, is called the length of the moment arm. So maybe I should use a lowercase m. So I've got a mass lowercase m at a distance x. If this is our fixed point, so it's like that center point on our seesaw. If I've got a mass m over here at this distance, it's going to have a tendency to rotate about P in this direction. And that moment is m times x. Now this definition of moment is slightly different from the one that you've seen in physics class. The one you've seen in physics class involves taking a force and multiplying it by the length of the moment arm. So what you've probably seen is mass times acceleration times x, but this is the math version. This is completely independent of gravity. The moments that we're talking about are going to be the same no matter what planet you're on. So it's really a characteristic of the geometry of the system and less about like fundamental forces or like gravity on Earth. So this is the moment of a single mass about a point P. It's just m times x. And this whole system is going to tend to balance if the moment from this side and the moment from this side are exactly the same. So let me give you a formula for the moment about the origin if you have a one-dimensional system. So let's say we're on the coordinate line, so on the x-axis. We've got all of these points, point masses. So we're assuming all of the mass is concentrated at a single point, and those point masses have mass m1, m2, m3, m sub 4, m sub 5, all the way through m sub n. So we've got n point masses. And these are their masses, and they're at particular locations. x1, x2, x3, x4, through x sub n. So our fulcrum, that center point, that balance point at the middle of the seesaw, that's where the origin is. We're going to treat this as the positive x direction, and this is the negative x direction, just like we're used to. So mass 1 is at x1, and mass 2 is at x2, and mass 3 is at x3, and so on. The moment about the origin is defined this way. It's m1 x1 plus m2 x2 plus m3 x3 and so on, and then you keep adding to get m sub n x sub n. So that's the sum as I goes from 1 to m of m sub I times x sub I. Now the shorthand notation that we use for this is m sub o for moment about the origin. Now this is going to be backwards from what you're used to in physics class. If this moment is positive, that means this sum of the moments on this side outweighs the sum of the moments on this side. The whole system is going to tend to rotate in a clockwise direction. I know that that is backwards from what you're used to in physics, and I'm so sorry that we're doing it differently, but we are doing it differently because we're leaving our positive x-axis that way, oriented that way. Now if the moment about the origin is negative, the system is going to rotate in a counterclockwise direction. Oops, I wrote positive, but I meant negative. Now, if I don't want the system to rotate at all, but I have all of these masses and they're at all of these locations, I can move my fulcrum. The place where I would move my fulcrum to so that everything balanced is called the center of mass. And that, for our one-dimensional system, which is just on a single axis, it's going to be given by x bar. Okay. So it's a new location, x bar, at which the fulcrum could be relocated so the entire system balances. So if m sub 0 is positive, we're going to rotate in this direction. If m sub 0 is negative, we're going to rotate in the counterclockwise direction. So we're going this way instead. If m sub 0 is 0, the moment about the origin is 0, we say that the system is in equilibrium. It's not tending to rotate at all. All the masses on this side, the moments on this side, are balanced by the moments on this side. Well, if the system's not in equilibrium, we can make it in equilibrium if we move the fulcrum to this new location, x bar. And it turns out that the new location for x bar is just the moment about the origin divided by the sum of the masses, or the total mass of the system. So we're going to take the sum of those masses times their locations. So that's giving us all of the moments, some of them positive on this side, some of them negative on this side. We're going to add them together, and we're going to divide by the total mass of the system. That's where we should put our new origin so that everything balances out. Okay, so that is 1D. This is the center of mass of a one-dimensional system. It's one-dimensional because we just have a single x-axis. I'm going to abbreviate center of mass as CM in 1D. Okay. So now let's do a very simple example. Let's say we've got some masses. So let's say our masses are M1 equals 7 kilograms, M2 equals 4 kilograms, M3 equals 3 kilograms, and M4 equals 8 kilograms. And they're at these locations on our axis. So -1, or excuse me, -3, -2, 3, or actually 5, and 6. Okay, so somebody might ask you to find the moment about the origin and then the center of mass. That's easy enough to do. The moment about the origin is just M1 x1 plus M2 x2 plus M3 x3 plus M sub 4 x sub 4. So we just get 7 times -3 plus 4 times -2 plus 3 times 5 plus 8 times 6. So it's -21 minus 8 plus 15 plus 48. So this is -29, and that's 63. So that's going to be 34. All right, so I guess the whole system tends to rotate clockwise. I know this is the opposite of physics class, and I'm sorry. But that's just because of the positive x-axis being where it is. So let's visualize this a little bit. So here's x equals 0. We've got our masses at x equals -3 and x equals -2. This is a mass, mass 1, and that's mass 2. And at x equals 5, we've got a mass of 3 kilograms. And at x equals 6, we've got a mass of 8 kilograms. So this is 3 kilograms, and that is 8 kilograms. And mass 1 is 7, and mass 2 is 4. And so this is our 0, that's our fulcrum point. So this is 2 units away, so the moment due to this single mass, mass 2, is just -8. If this is kilograms and these are all meters, let's say that they're meters, well then that's going to be -8 kilograms times meters right here. And this one, it's got a mass of 7 kilograms at -3 units, so it's 3 units away. The moment here is 21. So I've got 21 plus 8, that is 29, that's my measure of that moment that's tending to pull us in this direction. And that's that -29 right here when I do my calculation. Now on the other side, this single mass, mass 3, 5 units from the origin, even though it's only 3 kilograms, the moment due to that single mass is 3 times 5, that's 15. So that's 15, and the moment due to this mass of 8 kilograms, 6 units from the origin, that's going to be 48 units. That's huge. That 48 really pulls things this way, pulls things over to the right. So we've got a lot more moments on this side than this side. The moment to the right is larger than the moment to the left. So the whole system is going to pull that way. So this is a moment for a single mass. The moment about the origin is the sum of the moments for each individual mass. Okay, so we say, okay, that's what's going to happen in order to make our system, or that's what will happen if we leave our origin right here. This whole system is going to tend to rotate this way. If this is my little seesaw, it's going to rotate like this, except that middle point is going to be fixed. It's going to rotate that way. Now, if I want to move my fulcrum point to a new location so that everything would balance out, I think we've got to move it a little bit closer this way, don't we? So that those distances from the origin aren't so large on this side. So I'm expecting my x bar, my new center of mass, to be somewhere over here. It's going to be some x value between 0 and 5 is what I'm imagining. Let's see if my intuition is correct. X bar is the moment about the origin divided by the sum of the masses. Now we already found the moment about the origin. The sum of the masses is 7 plus 4 plus 3 plus 8. So it's 11 and 11, that's 22. So I've got 17 over 2, or times 2 over 11 times 2. And 17 over 11, which is a fine number between 1 and 2. But let's see what it is as an approximation. That's approximately 1.54. Okay. It's not nearly as far to the right as I expected it to be, but I guess that's because this mass of 8 kilograms is so large. Okay, so they're saying move that fulcrum point to 1.54. And now this distance times 4 plus this distance times 7 is going to be equal to this distance times 3 plus this distance times 8. This is my new balance point. Okay, in the next video we're going to look at moments for two-dimensional systems, and then we're going to talk about centers of mass and centroids for planar regions in the xy plane, which we call planar laminas.